All right, in this video lecture, I am going to lecture on section 6.1, which is an introduction to chemical bonding. So chapter 6 is all about chemical bonds and the different types. And then we're going to talk about, covalent bonds, ionic bonds, metallic bonding, shapes of molecules after they bond. So this lecture today is going to be about chemical bond and a little bit of an introduction. So let's just try to reference, get an idea of what we're in for here. Imagine getting onto this crowded elevator. Okay, so people are squeezing into this confined space. They come in contact with each other. Many people experience a sense of just being too close together. Okay, so now let's swap the people for atoms. When atoms get close enough, what do you think is going to happen? All right, well, take a look at what an atom is made up of. It's made up of subatomic particles, protons, neutrons, and electrons. Protons have a positive charge, electrons have a negative charge. And so outer electrons will actually repel each other. But at the same time, okay, the outer electrons are strongly attracted to the nuclei of that surrounding cell. And so eventually you're going to get to a point where those outer electrons are going to be attracted to other atoms, and that will determine what kind of bond will occur. So today's learning objectives. What's a chemical bond? Why do atoms form chemical bonds? What's the difference between ionic and covalent bonding? Why most chemical bonding is neither purely ionic or purely covalent. And then you will end it with classifying bond types based on electronegativity differences. And that's what your assignment will be based on. So atoms hardly exist as individual particles in nature, which means that you hardly see them in their pure state. So like a single oxygen atom, you're never going to find just a single oxygen atom in nature. You're hardly ever going to find one because it's readily reactive, it's unstable, it will react with other things. Okay, they will form bonds with other atoms. And so a chemical bond is this mutual electrical attraction between the nuclei of one atom and the valence electrons of a different atom, and that will bind them together. So when atoms bind to each other or form bonds with each other, they are either going to gain, lose, or share electrons. And so this might be like a little bit of review from biology or maybe a previous science class, but there are different types of bonds out there, and the ones we're really going to focus on first will be like covalent. I think section 6.2 is all about covalent, and then the next section is ionic, and then we'll talk briefly about metallic bonds. But ionic bonding is an electrical attraction between cations and anions. Remember, cations have a positive charge and ions have a negative charge, and so they are literally held together by opposite charges attracted to each other. In ionic bonds, electrons are being transferred from one atom to the other to fulfill the outer energy shell. So I have this visual concept. I don't think it's going to work because it's outdated. Oh, it does work. Here we go.
Ionic bonds begin to form when an atom whose outermost energy level is almost empty transfers an electron to an atom whose outermost energy level is almost full. The two atoms are strongly attracted to one another and bond because this new situation changes the atoms to ions of opposite charge. Particles of opposite charge are attracted to each other.
All right. So, covalent bond is what happens when you share electron pairs between the two atoms. And so when you share electrons, they are, I don't want to say owned, well, we're going to use the term owned equally by the two bonded atoms, but you'll learn that there are different types of sharing, but the electrons are being shared. So I have another short video here.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms. The first energy level in atoms can hold 2 electrons. By sharing electrons in a covalent bond, each hydrogen atom has a full outermost energy level. Water molecules are also held together with covalent bonds. Again, we see that covalent bonding gives each atom a full outermost energy level. The outermost energy level for hydrogen can hold 2 electrons. The outermost energy level for the oxygen can hold 8 electrons. In covalent bonds, the shared electrons move between the atoms that share them, forming a single electron cloud around both atoms.
All right, so because there were like 2 open spots on the oxygen and hydrogen just has 1 valence electron in its outermost energy shell, it's like, hey, I don't want to gain 7, I don't want to gain 1, you know what, I'm just going to like share this 1 with you. So now I have 2 and I'm fulfilled and happy, and oxygen had 2 missing spots, well then it gained 2, so now its outer shell is full and it's stable and equally happy. So the bond forms and it works. So how do you determine the bond? You're going to look at something called electronegativity values. Now this was touched briefly on chapter 5, looking at periodic trends. And the trend with electronegativity values is that as you move across a period, electronegativity values increase. And as you move down a group, they tend to decrease. Okay, so you will be classifying your bonds into 3 types of bonds: nonpolar covalent, polar covalent, and ionic bonds. So these 2 are two different types of covalent bonds where electrons are being shared, and ionic is the transfer of the electron. So what is a nonpolar covalent bond? You are binding electrons, these electrons involved in the bond are being shared equally by all the atoms involved. And so you get this balanced distribution of electrical charge. There isn't a slightly negative or slightly positive. It is neutral across the board. Okay. Polar covalent, you are sharing electrons, but you're sharing them unequally. And so the one that's hogging the electron, even though it's kind of somewhat sharing, becomes slightly negative, and the one that's, getting ripped off in the deal becomes slightly positive, because, charges develop when you have an equal number of protons to their electrons. And so you get slightly charged ends. One end will be slightly negative, and this is supposed to be a kind of a little S, like a Greek letter S. You'll see it on the next slide here, and then positive. And then ionic is the solid transfer of the electron, and it's the bond between 2 ions, right? One that's positive and one that is negative.
This diagram shows the relationship between the difference in electronegativity and the type of chemical bond between 2 atoms. The electronegativity difference between fluorine and cesium is 3.3. Because this is greater than 1.7, the bond is ionic. The fluorine atom has almost complete control of the electron, and the attraction between the 2 atoms is mostly electrical. The electronegativity difference between chlorine and hydrogen is 0.9. Because this is greater than 0.3 but less than 1.7, the bond is polar covalent.
Okay, I do just want to pause here for a second. Your book uses this figure. Okay, if you go on the internet, I have found 3 different images that have different values for the cutoff. Okay, so for the sake of my sanity, because this is what I was taught, and it was stated in a previous chemistry book, and it's based on your worksheet, we are going to use values 3.3 as the max. Okay, that doesn't change, but this value right here, it's not 1.7. It is now going to be 2.1. So if you get a value greater than 2.1, it will be ionic. If you get a value that is less than 2.1 but above, and this is another number we're going to change, 0.5. So from 0.5 to 2.1, we will classify that as polar covalent, and then anything below 0.5 will be non-polar covalent. Okay.
The chlorine atom has a greater attraction for the shared electron than the hydrogen atom. The electronegativity difference between hydrogen and hydrogen is 0. Because this is less than 0.3, the bond is non-polar covalent, and the 2 atoms share the electron equally.
Okay, so this is the diagram we are going to use. So values that are less than 0.5 will be non-polar covalent, and you can see we have even electron distribution, No slight charged ends at all. It is neutral. With our polar covalent values of 0.5 to 2.1, you see that we have a slightly positive and slightly negative end. There's that funky looking S. So because the electrons are hanging out more often with one atom, then this one kind of has a slightly negative charge and the other one's slightly positive. Ionic, there is no sharing of electrons. One electron is being transferred to the other, so now you have more electrons and protons, and we get a negative charge. And over here, because it lost that electron, you have more protons than electrons and has a positive charge, and opposites attract. So some electronegativity differences in some hydrogen halides, which means hydrogen bonded to halogens. Hydrogen's got a value of 2.1, fluorine 4.0, subtract the 2, 1.8. Okay, here's hydrogen and chlorine. Chlorine's value, crap, I don't even know. It's right next to fluorine, so it's like got to be 3 point something. Oh, so it's got to be 2 point. Did I say this was 2.1, 2.5? But anyways, the difference is 1. Okay, and so with that difference, take a look at that bond energy. Take a look at hydrogen and bromine. Take a look at hydrogen and iodide. But notice what happens with your electronegativity differences. Okay, the trend here is that it's decreasing. What happens to your bond energy? It also decreases. So what they're trying to say is that if you have a higher electronegativity difference, the bond energy, the energy required to break it, you're going to need a lot more of it. Okay, that's the trend. Now, how would we classify these? These would all be polar covalent. This is right on 0.5, and if it's right on 0.5, it's most likely going to be polar covalent. So just to recap, nonpolar covalent bonding, we are sharing electrons equally. The result is a neutral compound or molecule. Okay, take a look at this blurry picture of polar bears with penguins here. It says the clearest examples of nonpolar covalent bonds are those between identical atoms, such as H2, N2, O2, or Cl2. Bonds between atoms with nearly the same electronegativity value, such as carbon and hydrogen atoms, are usually also considered nonpolar. Remember, this is really a continuum, and there are some conventional distinctions that are somewhat artificial. Now, here we have two polar bears sharing an ice cream cone. Here we have two penguins sharing an ice cream cone. What does the ice cream represent? Your electrons, okay? What do the polar bears and penguins represent? Different types of atoms or elements. Now, polar covalent, okay, is where we are sharing unequally. Okay, two atoms still share bonded pairs of electrons, but those electrons are decidedly more attracted to one atom than the other. Examples include bonds between carbon and oxygen atoms, or between hydrogen and fluorine atoms, as you can see here. Electrons are hanging out with fluorine more than they are to hydrogen. So as a result, slightly negative ends, slightly positive ends. They're still sharing, just unequally. Okay, so this was a comparison between polar covalent and nonpolar. So here you can see that the overlapping spheres, circles, are like the same. Okay, over here you can see one is Hagen, hanging out with that electron more. Okay, this diagram is showing electronegativity charges. Okay, same thing, same concept, where one will be negative and red, so blue is negative, red is positive. Okay, and you can see that our fluorines at the bottom are kind of hogging all the electrons. I can still cut this molecule and get a negative and positive end. Now over here, this diagram represents that even though I have carbon and fluorine, I got to take a look at how all the molecules are arranged. Okay, so fluorine is going to be slightly negative, so negative, negative, negative here. Let me just draw this out, and then I'm going to have to close my door because my kids... What the hell? That was weird. Negative, and this is slightly positive, but I can't cut this molecule in any way where I'm going to end up with a magnet, a negative end and a positive end. So even though if I just looked at one individual carbon and fluorine bond, that would be considered polar, but because of the shape of the molecule, it is nonpolar. So shape does play a role. You don't need to know that right now. I am just foreshadowing things to come. Okay, let's take a look at some sample problems because we are now on the home stretch. So using electronegativity values listed in figure 3.1, which is found on page 159 in your book. Oh my God, I gotta get my book out. Yes I do. Yeah, Josie, I don't think you got your chem book, do ya? But that's okay, your worksheet has an electronegativity value, and I should not have said your name out loud. Go me. But anyways, if you don't have your chem book, no worries. I will gladly read the values out loud. So I'm on page 159. Okay, so we are looking at the bonding between sulfur and the following elements. So first off, I'm just going to write down the value of sulfur right above it. Electronegativity value of sulfur is 2.5. 2.5. Okay, now hydrogen's value is 2.1. Cesium, 0.7. And chlorine, 3. All right, so then it says we're going to subtract sulfur from all of these. Okay, so sulfur and hydrogen. So 2.5 minus 2.1. Let me get my arrow here. Electronegativity difference of 0.4. Okay, so here's 0.4. What's the bond type? You would say it's nonpolar. Which atom, hydrogen or sulfur, is more negative? Which one's hogging that electron? It's the one with the higher electronegativity value, sulfur. Okay. Okay, cesium. Sulfur and cesium. So we take 2.5 minus 0.7. We get a value of 1.8. So it's like somewhere around here. What's the bond type? Polar covalent. Which one? Sorry. Which one would be the more negative atom in this case? And that would also be sulfur. I don't know why I'm asking that question on the last one with nonpolar covalent. I think I'm just trying to, I don't know what I'm trying to do there. Okay, chlorine. Subtract the two, sulfur and chlorine, 2.5. Yeah, from 3. So you just always subtract from the larger one. You should not end up with negative values, is what I'm trying to say. You get 0.5. That one's right on the dot. So why did I put nonpolar covalent? I don't know. I think it's more likely polar covalent. But in this case, chlorine is going to be your more negative atom. Okay, so I'm going to pull up the worksheet here, which I did. I moved it somewhere. Here it is. It's going to look something like this. Okay? Some short answer. How are ionic bonds different from covalent bonds? How are polar covalent bonds different from nonpolar covalent bonds? How do we use electronegativity to determine polarity? Here I'm going to give you the answers. 0.5, 2.1, 3.3. What's the trend for electronegativity? I just said that in this lecture. For each of the following sets of elements, identify the element expected to be most electronegative. Now, you would need your book for this, but guess what? I included the electronegativity values on the worksheet. So you want to identify the element expected to be most electronegative. What do you mean? You need to circle that. I don't think I can write on this. Maybe I can highlight. All right, so which one of these? Potassium, scandium. So here's potassium, scandium, and calcium. Which one has the higher electronegativity? That would be SC. Oh, I can highlight. That was crazy. Okay. And then which one's the least electronegative? I'm going to put in green. So least electronegative would be potassium. And that's it. So you do the same thing for B and C. Down here, you are going to use the tables to determine what type of bond should be formed. I don't know if I can write. I guess we'll find out here. Yeah, maybe I can. Maybe I can't. Well, we'll just have to. Oh my God. Nope. Okay, nope, we're just going to vocalize this out. All right, so the value for phosphorus, P, is 2.1, okay? And silicon is 1.8. So 2.1 minus 1.8, I get 0.3. So my difference, I'd write 0.3. And then what's the bond type? Well, it's less than 0.5, so I would write nonpolar covalent, or NPC. Okay, and then you just do that for the rest of them. But that is the assignment. Easy peasy, lemon squeezy. Thanks for joining.